Assalamualaikum warahmatullahi wabarakatuh and good day to all my students. So I hope all of you are doing well and please take care of yourself. Right, for today's lecture, we will cover topic 5, which is ultraviolet and visible spectroscopy. So this topic involves calculation topics, and it is very interesting because we learn about the Woodward Fizer rules, which is required you to focus more, and also Beers-Lambert law. And it is very simple and interesting topics. Now we look at the topics first. First is about the molecular absorption and electronic energy transition, absorbing species, which is absorption by organic and inorganic, Woodward Fizer rules, the calculation of lambda max for alkene and carbonic compound, Beers-Lambert law, and the instrumentation, which are the single and double beam, and also the application in polymer characterization. Now we look at the introduction first. Ultraviolet and visible spectroscopy is the measurement of the weakening of a beam of light after it passes through a sample or after reflection from a sample surfaces. As we learned before this, in chapter 4, we have covered about the reflection, transmission, and absorption. Okay, so the absorption measurement can be at a single wavelength or over an extended spectral range. A phenomenon of interaction of molecule with ultraviolet and visible light, and absorption of photon result in electronic transition of a molecule, and electrons are promoted from ground state to higher electronic state. So we can conclude that the UV spectroscopy is a type of absorption spectroscopy in which light of the UV region lies between 200 to 400 nanometer is absorbed by the molecule. So the absorption of the UV radiation results in the excitation of the electron from the ground state to a higher energy state. Now we look at the functions of Uvv spectroscopy. First, UVV is used to detection of functional molecule in a sample. We can also detect the impurities in the sample. It is also for qualitative and quantitative analysis. Single compound without chromophore. We can determine the single compound without the chromophore. Drug with chromophoric reagent, and they also help to show the relationship between different groups. It is useful to detect the conjugation of the compound. Now we look at the principle of UVV spectroscopy. A molecule absorbs ultraviolet radiation of frequency, and the electron in that molecule will undergo transition from lower to higher energy level. So in the previous lecture, we did cover about the electromagnetic wave. Okay, so the electromagnetic wave are referred to by different names in accordance with their wavelength. That show that light usually refers to electromagnetic wave in the range spanning infrared radiation and ultraviolet radiation, but in some cases it refers only to visible light. So as we can see here, the visible range lies in 400 to 800 nanometer. So we can it is referred to as the visible light, and it is the light that we, as a human, we can see this light with the naked eye. For example, light with a wavelength of 470 nanometer here, it is a blue color. Okay, and the light with a wavelength of 500 plus, for example 540 nanometer, is a green color, and light with wavelength of 600 something, for example 650, it is a red color. So the visible light could be described as the kind of light that we humans are familiar with because our ability to see it. So we are familiar with the visible light region since these are the wavelength that the human eye is able to see. So this diagram show an approximation to the spectrum of visible light, and the color order is the visible region. We can remember by using your short form, your own short form. So from long wavelength to short, the colors are red. Okay, this is the longest wavelength here, and the color is the red, followed by orange, yellow, green, blue, indigo, and violet. Now we must place the visible light region into the rest of the electromagnetic spectrum. So it is perfectly possible to have wavelength shorter than violet or longer than red light. So let's recall our previous lecture, the relationship of frequency and the wavelength. So if the wavelength is longer, the frequency is lower. It is really important that you feel comfortable with the relationship between frequency and the wavelength. So each particular frequency of light has a particular energy associated with it. The higher the frequency, the higher the energy of the light. So light which has the wavelength of around 380 to 400 nanometer is seen as a sequence of violet colors, and various red color have wavelength around 625 to 740 nanometer, which one has the highest energy? Is it the red color or um, the color that have the wavelength 380 to 400? Between the red color and the um, violet color here, we can see that the light that with the highest energy will be the one with the highest frequency. That will be the one with the smallest wavelength. So violet has highest energy compared to the red color because violet color has smaller wavelength, right? So smaller wavelength will produce higher energy, and the longer or bigger wavelength will produce lower energy. So the energy can be calculated by the equation E equal to h nu. H is a Planck constant and nu is the frequency. So the higher the frequency, the higher the frequency, the higher the energy, right? So don't get confused with wavelength. This one is we have a lowest wavelength, but the frequency is highest. Okay, it will be contradict to wavelength. If wavelength lower, frequency higher. If frequency lower, wavelength will higher, right? Now we look at the mechanism in the absorption spectrum. When a sample is exposed to light, this is the step when the molecule in Uvv spectroscopy, it detect the color. Okay, first one, when a sample is exposed to the light, a fraction of the light energy will be absorbed by the molecule and occur when an energy that matches the energy difference between a possible electronic transition within the molecule. So it will display as a colored as in its own wavelength. So the electron will be promoted to the higher energy state orbital. From the ground state, it will excited to the higher energy orbital. And a spectrometer records the degree of absorption by a sample at different wavelengths. And the resulting plot of absorbance, we have A versus the wavelength lambda, is known as a spectrum. So this is what happens to the molecule when it absorbs the electromagnetic radiation EMR in this region will result in transition between electronic energy levels. As we can see, this is the nucleus of the molecule, and this is the electron. At the first stage, this electron is available or placed in a ground state. It is a comfort zone. So when the absorption of photon by the light, so the electron will promoted to the higher state, to the higher energy state orbital, because energy that matches the energy difference between a possible electron transition within the molecule has occurred. So it then will be excited to the excited state. Okay, now we look at the spectrum. Okay, so the y-axis is the absorbent, which is nominated by A, and the x-axis is a wavelength, which is lambda in nanometer times 10 to the power of -9. So lambda max, we can determine the lambda max, which is the maximum absorption of the compound of the molecule by using the UVVs. For example, compound isoprene is show the value for lambda max is equal to 222 nanometer. So the maximum absorption of the isoprene compound is at 222 nanometer. It is the wavelength at which there is a maximum absorption. Now we look at the electronic energy transition. Every molecule has a bond. The atom in a bond have their atomic orbital merged to form molecular orbital, which can be occupied by electron of a different energy level. Ground state molecule orbital can be excited to anti-bonding molecule orbitals. And this electron, when imparted with energy in the form of light radiation, will get excited from the highest occupied molecule orbital, HOMO, to the lowest unoccupied molecule orbital called LUMO. And the resulting species is known as the excited state or anti-bonding state. And the real location of the compound is on the ground state. And when it imparts with the energy, it will get into the excited state. Absorption of ultraviolet and visible radiation in organic molecule, for example, C3H4, is restricted to certain functional group because it contains carbon that contain valence electron of low excitation energy. The spectrum of a molecule containing this chromophore is complex. This is because the superposition of rotational and vibrational transition on the electronic transition give a combination of overlapping lines. This appears as a continuous absorption band. We look at the electronic transition in Uvv spectroscopy. We have a pi bonding. This one is pi bonding orbital to pi anti-bonding orbital that with star, and we have a non-bonding orbital which is n, and also we have a sigma electron, and we have single covalent bonds, double bonds, triple bond, and also lone pairs. And also we have T and F electron and charge transfer electron. Okay, D and F electron. This one is D and F electron. For D block elements are found in the middle of the periodic table. The D block elements are called the transition metal and have valence electrons in D orbital. So for the F element found in the 2 row at the bottom of the periodic table, we call it as the transition metal and have a valence electron in the F orbital.